In this exercise, we took a look at one of the basic elements of digital electronics, the logic gates, and the main focus is to see how the logic works in real time. A logic gate is a building of an electric circuit. Most gates have two inputs and one output. They implement a Boolean function, that is, they perform a logic operation on binary inputs and produce a single binary output, either high, which is 1, or low, which is 0. A truth table can be used to represent the Boolean expression of a logic gate. It shows each possible input with its corresponding output. Part 1, we used a truth table to figure out what type of gate the IC represented. We have 5 different types of logic gates with 2 inputs and 1 output. Here we had IC number 7400, and we figured out that it is a NAND gate. Then we had IC number 7408, which is an AND gate. Then we had IC number 7432, which is an OR gate. Then we had IC number 7486, which is an XOR gate. And then the last one is IC number 747266, which is an XNOR gate. In part 2, we tested out 2 ICs with different pin configurations to those in part 1. We first used IC 7404, which we figured out was a NOT gate. There was only 1 input and 1 output. Then we used IC 7402, which was a NOR gate. It had 2 inputs and 1 output.
Here we took a look at NOR and NAND gates and how we can connect them in a way that they replicate the function of other gates. We were supposed to find what type of each gate is by using the information from the truth tables in part 1 and 2. The setup of the circuit was kept the same as in part 1 and 2. For the NOR gates, we can replicate a NOT gate, a OR gate, and an AND gate. But for the NAND gate connections, we replicate a NOT gate, an AND gate, and an OR gate.
In this experiment, we built a half adder and a half subtractor, and took a look at an SR latch and a JK flip-flop. Adders and subtractors perform addition and subtraction of binary numbers in a circuit. They take in 2 binary digits and return sum and carry or difference and borrow. It is convenient to connect a LED bulb to each output to see if they take the value 1 or 0. SR latch and JK flip-flop are digital memory units that can be used to store a piece of binary information. A half adder takes in 2 binary inputs and provides an output of sum and carry, which gives 2 inputs and 2 outputs. The half adder is built with an XOR gate. The IC is 7486 and 1 AND gate, where the IC is 7408. Here you can see the function of the half adder. A half subtractor has an opposite function. It subtracts the 2 binary inputs and provides an output of difference and borrow. It is built like the half adder but with 1 NOT gate, where the IC is 7404, connected to one of the inputs and the AND gate. Here you can see the function for the half subtractor.
Even though SR latch has the quality of being simple, its biggest disadvantage is that when the clock is triggered, the inputs are not allowed to be high at the same time. It is considered an invalid input. An SR latch is made by cross-coupling two NOR gates, so that the output from one NOR gate becomes the input for the other one. When both set and reset are at 0, the stored state is unknown, and in our case the Q next LED lit up. In the table next to the video, you can see how Q and Q next behave with respect to the inputs from the set and reset buttons.
Okay, part 3 is the JK flip-flop. Here we have a characteristic table. It's useful for showing how J and K control the output. As you can see, it has 4 different states. The first one is when J and K are connected to ground. That's a hold or memory state where the current output for J will carry through to the next state. The second one is when J connected to ground and K is connected to VCC, which is a reset state where the next Q state output will be 0. The third one is when J connected to VCC and K is connected to ground, which is a set state where Q next will be 1. The fourth one is when J and K are connected to VCC, which is a toggle state where the Q next output will be the inverse of the current state output. Here we also have an excitation table. It's useful for showing what J and K are needed for a prescribed Q transition. And here you can see how we built the circuit. And here you can see the function of the circuit. The main difference between an SR latch and the JK flip-flop is that on the JK flip-flop, both inputs can be high. This results in the toggle state where the output alternates between high and low. Even though the JK flip-flop is an improvement on the SR latch, it still has some issues with timing. If the time it takes for the output Q to change state is greater than the time it takes for a clock input to trigger the next output, Q experiences unstable jittering.